In this podcast, we'll look at force diagrams for objects that are accelerating, and we'll apply Newton's second law, F equals ma, in order to calculate the acceleration of various objects. Let's look at example 1. Suppose the angle of incline is raised to 45 degrees. Calculate the acceleration of the penny. In an earlier vodcast, we looked at a penny on an inclined plane, and it was sliding at a constant velocity. Now suppose that we know the coefficient of kinetic friction is the square root of 3 over 3, and the incline is 45 degrees, and we'd like to get the acceleration of the penny. I'm going to start by drawing a force diagram for this problem. I've got the force of gravity, which I will break up into two components, parallel, perpendicular. I've got a normal force, which is congruent to my perpendicular force, and I've got a force of kinetic friction. Now, in this case, the force of kinetic friction, which is right here, is not equal to my parallel force. In fact, my parallel force must be longer than my force of kinetic friction. And that's what allows it to accelerate down the ramp. That parallel force being bigger is what makes the penny slide down the ramp. So I'm going to write a formula for the net force on the penny. The first thing that I'm going to look at is this parallel force acting parallel to the surface. The parallel force is pulling the penny down the ramp. The next thing I'm going to look at is the friction force, also acting parallel to the ramp. Those are the only two forces acting parallel to the ramp. Now I'm going to make some substitutions. I know that the net force is equal to mass times acceleration. I know that the parallel force is equal to Fg sine theta. And I know that the friction force is equal to mu times Fn. But wait a minute, Fn is equal to F perpendicular, which is Fg cosine theta. I also know that Fg is equal to mass times gravity, so I'm going to rewrite this whole equation. Ma equals mg sine theta minus mu mg cosine theta. Okay, so finally I get to calculate the acceleration of the penny. Notice I can factor mass out of each term of the equation, and the acceleration is going to equal g times the sine of 45 minus the coefficient of friction, which is the square root of 3 over 3, times g times the cosine of 45. The sine of 45 and the cosine of 45 are both the square root of 2 over 2. So the acceleration is going to be g times the square root of 2 over 2 minus g times the square root of 3 over 3 times the square root of 2 over 2. And we can do one more simplification. I'm kind of running out of room. So we've got acceleration equals g times the square root of 2 over 2 minus g times the square root of 6 over 6. Let's try another one. A man pulls a box with a weight of 250 newtons across the floor. He applies a force of 100 newtons at an angle of 45 degrees to the horizontal. The coefficient of kinetic friction is 0.1. Calculate the acceleration of the box. Start with my force diagram. Fg is 250. He applies a force of 100 newtons at 45 degrees. right away I'm going to think about the components. FAX is going to be 100 divided by the square root of 2. FAY is going to be also 100 divided by the square root of 2. This is a special right triangle with a 45-degree angle. The normal force then is going to be less than the force of gravity. I'll come over here to calculate normal force. The normal force is going to be equal to the force of gravity minus FAY. The normal force is going to be equal to 250 minus 100 over the square root of 2. Finally, got friction. Oops, and I drew it too long. I want to draw it shorter than FAX. Otherwise, the block won't be accelerating. The force of friction is equal to the coefficient of friction times the normal force. Coefficient of friction is 0.1, and the normal force we just determined is 250 minus 100 over the square root of 2. So, all of that just to get to this point. The net force on the box. The net force on the box is a horizontal force. It's the difference between FAX and FK. The net force on the box is equal to 100 over the square root of 2 minus FK, which we said was 0.1 times 250 minus 100 over the square root of 2. I will pause at this point to get out a calculator, and I will be solving the rest of this problem with a calculator. Okay, so I've got my calculator handy, and I'm calculating 100 divided by the square root of 2 is 70.7. This component, or this term, is equal to 17.9. 70.7 minus 17.92 gives us 52.79. And that's equal to the mass of the box times its acceleration. If the box has a weight of 250 newtons, I can determine its mass by taking 250 newtons divided by 9.81 meters per second squared. So the mass of the box will be 25.5 kilograms times the acceleration equals 52.79 newtons, and now I divide to get, to get 2.07, or about 2.1 meters per second squared. Let's keep going. Let's take a look at a different kind of acceleration, a vertical acceleration. Example 3 is something called an Atwood machine. I've got two blocks hanging over a pulley, and the pulley is free to rotate. In this scenario, we're going to assume that the pulley itself is frictionless and massless. This is an unrealistic expectation, but we often idealize things in an entry-level physics course. So we're just going to focus on the two masses. We'd like to calculate the acceleration of the block system. So I'm going to draw a force diagram for M2. So M2 has two forces on it. It has the force of its own weight, which is equal to M2 times G. And then it also has a tension force. Now the tension force is less than the force of gravity, and this is going to cause the block to accelerate downward. The tension force in this string is caused by M1. And that tension force, therefore, is equal to M1 times G. So if we wanted to find the net force of this system, and if I assume that that M2 is the bigger block, then I can say that the net force, which is directed downward, is equal to Fg minus Ft. And net force is typically equal to mass times acceleration. But in this situation, the mass that's accelerating is not just M2, but it's actually both masses accelerating, which means that when I plug into MA, I need to use both masses added together. I'll make a substitution for Fg. It's equal to M2G. And Ft then is M1G. So when we solve this for acceleration, I'm going to end up dividing both sides by M1 plus M2. So my final answer will be that the acceleration is equal to M2G minus M1G all over M1 plus M2. If you'd like to factor out the G, you can, but for now I left it as is. Let's look at another example of vertical acceleration. Call this an elevator problem. A person with mass m is in an elevator. The elevator accelerates upward at 2 meters per second squared. What is the apparent weight of the person? Okay, I'm going to draw the person as a block. And the elevator is accelerating upward, which means that the upward force, the tension force, must be greater than the actual weight of the person. So in order for the elevator to accelerate upward, there must be a greater upward force than downward force. So in this case, my net force is going to equal tension minus Fg. So the mass of the person times their acceleration is going to equal the tension force minus their mass times 9.81. So their mass times 2 equals the tension force minus their mass times G. And basically, to solve for their apparent weight, what I would end up doing is I would solve for Ft. And to do that, I would add mg to both sides. So I would end up with 2m plus mg equals Ft. And what you'll see here is if mg is the weight of the person, they feel heavier than that when they're accelerating upward in an elevator. Maybe you've had that experience yourself.